Welcome to IT.Solution, your total network, system, firewall, and security partner.
Welcome to this explainer on ITN Module 13, where we're going to explore the invisible diagnostic nervous system that literally keeps the entire internet running. You know, when we think of networks, we usually just picture massive amounts of data flowing back and forth, right? Web pages loading, media streaming, email sending. But beneath all of that heavy lifting, there's actually an entirely different conversation happening behind the scenes. It's this constant, vital pulse of communication that allows the network to monitor its own health. So today, we're demystifying exactly how this foundational protocol works.
Let's kick things off by asking a seemingly simple question. How do devices actually know they're connected to each other? Think about walking through a pitch-black room. You can't see a thing, so you reach your hands out, kind of feeling for walls or open doors. If you happen to stub your toe, which, let's be honest, is the absolute worst, your pain receptors instantly fire a message back to your brain saying, hey, the path is blocked. Well, computer networks need a similar mechanism. They have to feel for connections, report pain, and know exactly when a pathway is broken. And they do this using a method that's actually really similar to sonar.
And that brings us to ICMP, or the Internet Control Message Protocol. Think of ICMP as that foundational nervous system we just talked about. It's the Layer 3 control protocol, which means it operates right alongside your standard IP packets. But what makes it so incredibly unique is that it doesn't rely on any higher-level application protocols like TCP or UDP. It honestly doesn't care about what web browser you're using or what app you're running. Its one and only job is to report errors and provide immediate, raw feedback on IP packet processing.
Here's our roadmap for today. We're going to cover 1. The network's nervous system, 2. Diagnostics with ping and traceroute, 3. The IPv6 ICMP upgrade, and 4. ICMP security and vulnerabilities.
Section 1. The network's nervous system. What's really fascinating here is the precise vocabulary the network uses to communicate a failure. When a data packet fails to deliver, it doesn't just, disappear into a black hole. ICMP actually sends back highly specific messages. For instance, if a router doesn't have a route to a specific IP, it fires back a destination unreachable message. And this message even includes a specific code, like code 0 for a net unreachable, or code 3 if the specific port is unreachable. Another one you'll see a lot is time exceeded, because IP packets aren't allowed to just loop around the internet forever. If their time expires before reaching the destination, a time exceeded message gets sent straight back to the source. It tells you exactly what went wrong.
Moving on to Section 2, Diagnostics, Ping and Traceroute.
This brings us to the most famous network tool of all time, ping. You've got a host sending an echo request to a target, and that target responding with an echo reply. It is literally echolocation for digital networks. By firing off an ICMP Echo Request, ping lets you test basic Layer 1, 2, and 3 connectivity all at once. You're verifying your network cable is plugged in, your switch is forwarding frames, and your router actually knows how to route that IP packet all the way to the destination and back.
But here's the thing, you don't just ping randomly. A good network technician uses it progressively to isolate exactly where a connection is dropping. You start by pinging your own loopback address, which is 127.0.0.1 for IPv4, or ::1 for IPv6. That just proves your own machine's internal network stack is actually functioning. Next, you step out and ping your default gateway, which is usually your local router, to test if your local network is healthy. And finally, you ping a remote host out on the internet. If steps 1 and 2 work, but step 3 fails, well, you instantly know the problem isn't your computer or your local switch, it's somewhere out there on the wider internet.
So, the crucial takeaway here is that while ping tells you if you can reach the destination, traceroute tells you exactly how you get there. Ping is great for measuring the basic success rate and the total round-trip time. But if a ping fails, it doesn't tell you which router dropped the packet. That is exactly where traceroute comes in. It tests the step-by-step path, identifying every single router, or hop, along the way, so you can locate the exact device causing the problem.
I absolutely love how Traceroute pulls this off, because it basically weaponizes standard network rules. See, every IP packet has a time to live, or TTL, value attached to it. Every time a router forwards a packet, it drops that TTL number by 1. If the TTL hits 0, the router kills the packet so it doesn't loop forever, and it sends an ICMP time exceeded message back to the sender. Traceroute intentionally sends packets with a TTL of 1, forcing the very first router to send an error. Then it sends a TTL of 2, forcing the second router to send an error. By doing this sequentially, it forces every single router along the path to expose itself via an ICMP error. It's brilliant.
Section 3. The IPv6 ICMP upgrade. The leap from IPv4 to IPv6 was a huge deal. It wasn't just about handing out longer IP addresses. It was a major architectural shift. The creators of IPv6 decided to streamline things by pulling functions from older, separate protocols and baking them directly into ICMPv6. For example, the old Address Resolution Protocol, or ARP, that we used in IPv4 completely replaced. It was swapped out for a brand new ICMPv6 feature called the Neighbor Discovery Protocol, or NDP.
Check this out. When an IPv6 device boots up, it doesn't even always need a DHCP server to find its way. Instead, it fires off an ICMPv6 router solicitation message, basically shouting out, "Hey, are there any routers out there?" The local router hears this and dynamically replies with a router advantage message. That RA message hands the device its network prefix, its default gateway, and literally everything it needs to configure its own global IP address dynamically.
Building right on top of that, once the computer knows its own IP address, it still needs to find the MAC addresses of other devices on the local link to actually send frames. In the old IPv4 days, this meant sending a noisy ARP broadcast. But now, in IPv6, it uses ICMPv6 neighbor solicitation and neighbor advertisement messages. Your PC simply asks, "Who has this IPv6 address? Send me your MAC address," and the target device replies directly. It is so much clearer, it's more efficient, and it completely handles device mapping on the local link.
Which brings us to our final section, Section 4, ICMP Security and Vulnerabilities.
Okay, we have to talk about the dark side here. Because what happens when these incredibly helpful diagnostics are weaponized? The reality is, hackers absolutely love ICMP. They can twist these control messages to map out your entire network. A simple sweep of ICMP Echo requests can verify exactly which vulnerable hosts are online. Unreachable messages, those can be used to scan your firewall rule sets. Hackers can even manipulate ICMP redirect messages, which are normally meant to tell a host about a faster router path, to instead lure a target into sending all its traffic through a compromised device. Boom, you've got a seamless man-in-the-middle attack. They can even inject bogus routes.
Because of these really severe threats, you literally cannot just leave ICMP wide open to the internet. Network admins have to enforce strict security. This usually means using access control lists, or ACLs, to filter ICMP traffic right at the network edge. So you might allow echo replies back inside, but you're definitely going to block external echo requests coming from the outside. On top of that, robust networks utilize intrusion prevention systems, or IPS, to actively intercept traffic, evaluate it against known threat signatures, and drop malicious ICMP probes before they ever touch the internal network.
So as we wrap up this explainer on ITN Module 13, I want to leave you with a provocative thought. As you dive deeper into IT and you start designing your own networks, how are you going to handle this protocol? How will you balance the critical everyday need for internal diagnostic visibility against the absolute necessity of external security? If you block too much, you're flying blind when things break. But if you block too little, you are handing attackers a roadmap to your data. Finding that perfect balance? That is the true art of network engineering. Thanks for joining me today, and keep exploring the incredible architecture that connects our world.
Thank you for watching. See you in the next episode.